Somewhere in the reflected sunlight bouncing off Pluto's frozen surface, there's a very specific color of infrared light that simply isn't there. Not faint, not ambiguous. A clean, measurable gap in the spectrum at a precise wavelength, and it doesn't match a single known substance in any chemical database astronomers have checked it against, despite the fact that this particular kind of reference library has successfully identified nearly everything else researchers have ever pointed a telescope at. And the exact same missing light shows up on a completely different world, more than 800 million miles away. Stick around, because I'm going to walk you through exactly what the James Webb Space Telescope just found on Pluto, why researchers currently can't identify what's causing it, and why the very same mystery is turning up in the last place anyone expected. And if you want more of these deep dives into real published research instead of recycled headlines, go ahead and subscribe now, because there's a lot more coming out of the far edge of our solar system. To understand why this particular finding has scientists genuinely puzzled rather than just mildly curious, you first need to understand how researchers actually figure out what a distant world is made of without ever landing on it. When sunlight hits an icy surface like Pluto's, different chemical compounds absorb very specific, narrow slices of that light, each one leaving behind its own unique fingerprint in the reflected spectrum that eventually reaches a telescope's instruments. Scientists have spent decades building an enormous reference library of exactly what these fingerprints look like for every ice and organic compound they've ever measured in a laboratory. Which means that when starlight or sunlight bounces off a distant world and comes back missing a very specific wavelength, researchers can usually just look up which known substance produces that particular gap and identify the surface material with real confidence. This entire method depends on one basic assumption holding true, that whatever is absorbing a particular wavelength of light out in space has already been measured and cataloged here on Earth first. That assumption turns out to be remarkably solid the vast majority of the time, since planetary scientists have spent decades painstakingly building up reference spectra for essentially every simple ice, gas, and organic compound plausible enough to exist on a cold outer solar system world, testing each one under laboratory conditions designed to mimic the extreme cold and near vacuum found on places like Pluto and Titan. When a telescope like Webb picks up a new absorption feature, the very first step researchers take is almost always to run that signal against this existing library. And in the overwhelming majority of cases, they get a match within minutes. It's precisely because that process usually works so cleanly and so quickly that a genuine miss, an absorption feature with no match anywhere in the existing literature, stands out as something worth taking seriously rather than dismissing as an instrument artifact or a data processing error. That system works remarkably well most of the time. But in June of 2026, a research team led by planetary scientist Bruno Bézard published a study built around exactly the kind of measurement that system is supposed to handle easily, and it didn't work. The team had been using Webb's exceptional sensitivity to examine a relatively unexplored slice of the infrared spectrum, a narrow atmospheric window between roughly 4.9 and 5.4 micrometers, chosen specifically because it's less affected by atmospheric haze than other wavelengths, meaning it offers an unusually clear look directly at a surface. They pointed that capability first at Saturn's giant moon Titan, a world so thick with orange smog that its actual solid surface has remained one of the most stubbornly difficult things in the solar system to study directly ever since Titan was discovered. What they found was an absorption feature centered precisely at 5.113 micrometers, cutting into Titan's reflected light with a depth of about 6 to 7%, meaning that specific sliver of light was being swallowed up by something on or near the moon's surface far more strongly than any known component of Titan's atmosphere or surface ice could account for. The team did what any careful research group would do next. They built a detailed radiative transfer model, a type of simulation that accounts for every gas and haze particle already known to exist in Titan's atmosphere, and checked whether that model could reproduce the missing light on its own. It couldn't. The absorption simply wasn't there in the simulation, meaning whatever was causing it in the real data wasn't accounted for by anything scientists already knew was present on Titan. If you're finding this as strange as the research team clearly did, drop a comment and let me know, because it genuinely helps me figure out what other space stories are worth covering next. That alone would have been a notable, if narrow, finding about one moon of Saturn. What turned it into something considerably stranger is what happened when the same research team decided to check whether this same signature showed up anywhere else. They pulled archived Webb data of Pluto, originally collected back in May of 2023, using two of the telescope's instruments, the near-infrared spectrograph and the mid-infrared instrument, and looked for the same specific gap in the spectrum. It was there, the exact same absorption, centered at that same precise 5.113 micrometer wavelength, present in Pluto's reflected light despite Pluto and Titan being fundamentally different kinds of worlds, orbiting completely different planets in completely different regions of the solar system, separated by roughly 1 billion miles of empty space. The signal wasn't identical between the two worlds, though, and that difference turned out to be almost as interesting as the discovery itself. On Pluto, the absorption depth came in similar to Titan's, somewhere around 4 to 5%, but the actual width of that gap in the spectrum was roughly 3 times broader than what the team measured on Titan. In spectroscopy, the width of an absorption feature carries real physical meaning. It's shaped by the exact molecular environment the absorbing substance is sitting in, whether it's pure or mixed with other materials, whether it's crystalline or more loosely structured, and what temperature and pressure conditions it's experiencing. A signal that's the same core wavelength but a noticeably different width on 2 different worlds suggests researchers may be looking at the same underlying chemical compound, but existing in physically different states or environments on each surface, rather than 2 coincidentally similar but unrelated substances. Once the team had confirmed the signal was real and present on both worlds, they did the obvious next step. And this is the part that turned a curious detection into a genuine scientific mystery. They combed through the existing scientific literature, systematically checking the absorption spectra of every ice and organic compound, previously measured in laboratory settings that could plausibly exist on either Titan or Pluto, searching for anything that produced a matching signature at exactly 5.113 micrometers. According to the published study, they didn't find a clean match. The researchers explicitly stated that they could not find any previously documented absorption band in the existing literature corresponding to the location of what they were observing on either world. In the paper's own words, this appears to be a genuinely unidentified feature, not simply an overlooked or under-cataloged version of something already known. That doesn't mean the team came up completely empty-handed, though. Rather than leaving the finding as a total blank, the researchers worked through a short list of chemical candidates that could plausibly, even if not perfectly, explain a signal in roughly the right location. The most promising candidates belong to a family of molecules called allynes, a specific class of hydrocarbon compounds that share a particular kind of double-bonded carbon structure. Beyond that primary candidate, the team also flagged several other possibilities as worth investigating further if mixed together with other compounds already known to exist on these worlds, including benzene, a compound called ketene, and considered less likely, acetylene, a gas already confirmed to exist in smaller amounts in Titan's atmosphere. None of these candidates produced an exact, confident match on their own. They represent the team's best current working hypotheses, explicitly framed as provisional rather than confirmed, while the actual identity of whatever is producing the signal remains genuinely open. The team also took a closer, more technical look at exactly why the Pluto and Titan versions of this signal differ in width, since that detail carries real scientific weight of its own. According to the published analysis, the equivalent width of the feature, essentially a measurement of its total absorbed area rather than its raw depth, actually comes out roughly the same on both worlds once researchers account for the different instruments and viewing conditions involved. That consistency in equivalent width, paired with the difference in how that absorption is spread out across the spectrum, points toward the 2 worlds hosting the same underlying compound. But in a different physical state at the molecular level, rather than genuinely different amounts of it. Researchers also specifically examined unpublished laboratory measurements of acetylene ice mixed at low concentration into nitrogen ice, since Pluto's surface is dominated by nitrogen ice in a way Titan's isn't, and found that this specific mixture shifts the resulting absorption slightly compared to pure acetylene ice on its own, a detail that keeps acetylene provisionally on the list of candidates worth continuing to investigate, even though the team considers it a less likely explanation than the allyne family overall. It's worth pausing here to explain why finding something like this on Titan specifically carries extra weight, beyond just adding one more mystery molecule to a list. Titan's surface has been almost uniquely difficult for scientists to study directly, precisely because its thick, hazy nitrogen and methane atmosphere scatters and absorbs so much light that getting a clean look at the actual solid ground underneath has always required extremely narrow, carefully chosen windows in the spectrum, where the haze interferes the least. That's exactly why this research team specifically targeted the 4.9 to 5.4 micrometer range in the first place, because it's one of the broadest, cleanest windows available for seeing past Titan's atmospheric haze and down to its actual surface chemistry. Finding a completely unexplained absorption feature in exactly the kind of data that was supposed to finally give researchers a clearer picture of Titan's surface composition is, in a sense, both a genuine breakthrough in observational technique and a brand new open question, arriving in the very same discovery. Pluto's situation is a little different since its atmosphere is far thinner than Titan's, closer to what scientists sometimes describe as a thin, Titan-like haze rather than Titan's dense, opaque blanket of smog. That thinner atmosphere generally makes Pluto's surface easier to study directly than Titan's. But Pluto's disk, as seen from a Webb, is also extremely small, small enough that the mid-infrared instrument's individual detector pixels couldn't fully resolve it, meaning the spectrum researchers worked with represents an average blend of light across Pluto's entire visible surface and atmosphere combined, rather than a detailed map of exactly where on the surface this mystery signal is strongest. That limitation is part of why the research team has specifically called for additional, more targeted observations going forward, ideally ones that could map out how this absorption feature varies across different regions of each world, information that could help narrow down the list of chemical candidates considerably. This limitation is worth explaining a little further because it highlights just how much observing distant worlds depends on the physical size of the instrument doing the looking. Pluto, seen from Webb's vantage point roughly 4 billion miles away, appears astonishingly tiny, spanning an angle in the sky measured in a fraction of a single arc second, smaller than the smallest resolvable unit any of Webb's individual detector elements can distinguish on their own for this particular instrument. That means every measurement researchers get back from Pluto through this channel is necessarily an average, blending together light from the sunlit hemisphere. Any visible atmospheric haze and whatever surface variation exists across the whole visible disk, all compressed into a single combined spectrum. Untangling exactly which specific region of Pluto's surface is responsible for the strongest version of this absorption feature simply isn't possible with the current dataset, and would likely require either a much longer observing campaign stacking multiple viewing angles together, or an instrument specifically designed to resolve Pluto's disk in finer detail than Webb's current mid-infrared capability allows. There's a genuinely exciting piece of context that makes this particular mystery unusually likely to actually get resolved, rather than simply lingering as an open question indefinitely. NASA's Dragonfly mission, a rotorcraft lander currently scheduled to arrive at Titan in the mid-2030s, is being sent specifically to conduct detailed, on-the-ground chemical analysis of Titan's surface at multiple different locations. Dragonfly carries an instrument called the Dragonfly Mass Spectrometer, built specifically to identify the chemical composition of surface and near-surface material through direct, in-situ sampling rather than remote spectroscopy from orbit or from Earth. According to the research team's own paper, several of their leading candidate molecules for this mystery signal, including alans and benzene, should be detectable by that instrument once Dragonfly actually reaches the surface and begins taking measurements. There's one interesting caveat worth mentioning, though. Acetylene, one of the less likely but still considered candidates, is a relatively volatile compound. And according to communication the research team had directly with Dragonfly mission scientists, that particular molecule might not survive intact through the mass spectrometer's specific analysis process, even if it does turn out to be present, meaning a clean detection of every candidate isn't guaranteed, even with a spacecraft sitting directly on Titan's surface. That timeline is worth sitting with for a moment, because it means this specific mystery, a genuinely unidentified molecule sitting on two different worlds, nearly 1 billion miles apart from each other, might actually get a real, direct, ground truth answer within the coming decade, rather than remaining a purely theoretical debate conducted entirely through remote spectroscopy. That's a genuinely unusual position for a fresh planetary science mystery to be in. Most open questions about distant worlds have no realistic near-term path toward direct confirmation, simply because there's no mission currently planned or funded to go check. This one does, and the same team that found the mystery signal has already identified the exact instrument that stands the best chance of eventually solving it. In the meantime, this discovery adds to what has already been a remarkably active few years of Webb-driven Pluto research. The telescope's earlier work confirmed that Pluto's high-altitude blue haze functions almost like an active refrigerator, radiating heat away from the dwarf planet's thin atmosphere rather than trapping it. A finding published in Nature Astronomy that gave scientists their first real look at what researchers have described as a genuinely new kind of planetary climate. Separate Webb observations of Pluto's large companion moon Charon confirmed the presence of both carbon dioxide and hydrogen peroxide frozen onto its surface, adding further detail to an already complex picture of the Pluto system's chemistry. This newest finding, an entirely unidentified molecule hiding in plain sight, in data that had already been sitting in Webb's archive since 2023, is a reminder that even data astronomers have already collected and analyzed once can still be hiding genuinely new discoveries, simply waiting for someone to look at it from the right angle, using the right narrow slice of the spectrum nobody had thought to check quite this carefully before. So what does all of this actually add up to? A telescope built to study the earliest galaxies in the universe pointed its instruments at two small, cold, distant worlds and found the exact same unexplained gap in their reflected light. a signature that doesn't match anything in the existing catalog of known space chemistry, showing up in data that had already been sitting archived for years before anyone noticed it. It's worth sitting with just how routine this particular discovery looked at first, before it turned into something genuinely puzzling. Nobody set out on this project hoping to find a brand new, unidentified molecule. The research team was simply trying to get a clearer look at Titan's long-obscured surface, using a narrow, carefully chosen slice of the infrared spectrum that happened to offer unusually good visibility through the moon's thick atmospheric haze. That kind of incremental, methodical observational work rarely makes headlines on its own, and yet it's exactly the kind of careful, patient science that keeps turning up genuine surprises, simply because nobody had looked quite this closely in quite this specific wavelength range on either of these two particular worlds before. The mystery didn't announce itself. It was sitting quietly in already collected data, waiting for the right combination of instrument sensitivity and researcher curiosity to notice it was there at all. Whether the answer turns out to be a family of simple hydrocarbon molecules called alenes, some mixture of already known compounds behaving in an unexpected way, or is something nobody has properly considered yet, researchers may not have to wait too many more years to actually find out once a spacecraft finally sets down directly on Titan's surface and takes the kind of close, direct measurement that no telescope, however powerful, can fully replace. If stories like this one, grounded in real published research, rather than exaggerated headlines, are what you want more of, subscribe to this channel and turn on notifications, because there's a real chance the next round of Webb data adds another genuinely strange piece to this puzzle before Dragonfly ever gets the chance to settle it directly. Thanks for watching, and I'll see you in the next one.